In this video, we'll be talking about arc lengths, or how to find the length of a curve. The first part of the video will go over the formula that we use to find the arc length. For example, we see here on the screen a curve, which we'll call f, and we've identified 2 points on the curve, a point A and a point B. And what we'd like to do is find out how long is the path along the curve from the point A to the point B. Keep in mind that if the point A and point B were connected with a straight line, we could use the distance formula, or the Pythagorean theorem, to help us find the distance between the 2 points. But because this is a curve rather than a straight line, we have to use something different. And in order to do this, we're going to use integrals. And like other things that we do using integrals, we're going to start by chopping things up into little pieces. In this case, we're going to chop the curve up into a bunch of little pieces. Once we chop the curve up into a bunch of smaller pieces, notice that any one of the smaller pieces is closer to being a straight line than the entire line segment is. And the smaller we make the piece, the closer it's going to be being a straight line. So because of that, what we will do is use the formula to find the length of a straight line in order to help us find the length of each line segment. And then using the integral, we'll take the limit as the number of segments goes to infinity and add up the length of infinitely many, infinitely small line segments. If we just pretend that each little piece is a line segment, we can use the Pythagorean theorem. So you can see here that I've drawn in a little green triangle that's going to help us find the length of the hypotenuse of the triangle as one of the pieces of our line segments. But it's pretty small, so let's draw it again bigger so we can see what the triangle looks like. After we draw it bigger, it's easier to see that the horizontal change in the triangle, that horizontal side, has a length that's really just a change in x, and the vertical side of the triangle has a length that's a change in y. So if we want to find the length of the hypotenuse of the triangle, which is the part of the triangle that follows the curve, and that's what we're trying to find the distance of, we can just use the Pythagorean theorem. When we do, we get that the distance is equal to the square root of the change in x squared plus the change in y squared. So our curve that we're trying to find the length of is made up of a bunch of tiny line segments that when we take the integral they'll become infinitely small, and the length of any one of them could be found by doing the square root of the change in x squared plus the change in y squared. So now, in order to find the length of the entire curve, we're going to use an integral and add up a bunch of those little triangle hypotenuses. You can kind of imagine that every single little segment that we've divided the graph into has one of these little triangles, and the length of each one is just the square root of a change in x squared plus a change in y squared. So the length of the curve, which we'll call L, is going to be the integral from a to b of the square root of dx squared plus dy squared. Now notice when we put it into an integral, our delta x changes to a dx. That's because when you put it in an integral, we've taken the limit as the norm of the partition goes to 0, which means that each of those little segments are infinitely small, and we represent that change with a dx because it's an infinitely small change instead of a delta x. Now, in order to make this formula usable, we need to rewrite it. It looks kind of funny. Notice we've never seen a formula that has the dx and the dy inside the middle of the formula like this. So we need to rewrite it. We need to have a dx at the end. And so in order to put a dx at the end, like we're used to, we're going to take this equation and we're going to multiply and divide by dx, which gives us this. Now, in order to simplify it, we want to take that dx that's in the denominator and put it inside the square root that's in the numerator. So if we take the dx in the denominator and square it and put it under the square root, we get something that's equivalent because the square root of dx squared is just dx. And that gives us this. And now we'll take the fraction that's inside the square root and split it into 2 pieces. So we'll keep our common denominator common to both pieces of the fraction, but we'll get dx squared over dx squared plus dy squared over dx squared. And now, just to finish simplifying, dx squared over dx squared we know is equal to 1, and then dy dx is just the derivative, so the next part what we have really is the derivative, dy dx squared. So this formula here is a more usable formula, but all it really is just the Pythagorean theorem rearranged inside the integral. So the length of the curve can be given by the integral from a to b of the square root of 1 plus the derivative squared dx. And this will be the formula that we will use when we find the arc length. In our first example, example 1, we will find an arc length using this formula. This problem asks for us to find the length of y equals 3x squared from x equals 1 to x equals 4. Let's start by drawing a graph. I'll use Mathematica so we can see it on the computer, but let's draw a graph of y equals 3x squared and identify the point where x equals 1 and the point where x equals 4. So what we're trying to find here is the length of the curve in between the 2 points that are represented with blue dots on the curve. So we'll use the formula that we just learned for the length of the curve, where we do the integral from a to b of the square root of 1 plus the derivative squared dx. So when we apply this formula to this specific problem, we get that the length of the curve is equal to the integral from 1 to 4. 1 to 4 is because that's the part of the curve that we're trying to find the length of. And then of the square root of 1 plus the derivative, which for this particular function, we know the derivative is 6x, so we'll put a 6x in where the derivative goes, and then we square that, and then put a dx at the end. Now the square root actually makes this integral rather difficult to evaluate by hand, so we're going to be using Mathematica to evaluate all of the integrals in this problem. So I'm going to switch over to Mathematica and show you how to evaluate this integral using Mathematica. In order to evaluate a definite integral in Mathematica, we can use the palette. If you go to Palettes and then Basic Math Assistant, it will come up with the Basic Math Assistant, and you go to the Advanced tab, and you'll see on the Advanced tab right here, there's an integral button. So if you push that button, it puts in a nice template for you, so now we can just type in the equation. So notice that the lower limit of the integral is blue right now. That means that's where it's ready to type. So we just hit the 1, and then we hit tab, and then we type the 4, and then we hit tab. And now we go back to our palette, and in the palette we find the square root, which is right here. So you do the square root of, and now underneath the square root is blue, so that's where we're typing. So we do 1 plus parentheses 6x, close the parentheses, squared. And then we hit tab, and here we need to tell it that the integral is with respect to x. So we do dx. Now this integral gives an exact answer, and the exact answer is rather messy and hard to interpret. We'd rather have a decimal answer on this one rather than an exact answer. So to force Mathematica to give me a decimal answer, I'm going to include a //n, and then hold down Shift and push Enter, and that gives me the answer for the length of the curve. So based on what we found in Mathematica, we know that the length of the curve y equals 3x squared between x equals 1 and x equals 4 is 45.12 units. In example 2, we'll use the arc length formula to find the length of a curve. This problem asks for us to find the length of y equals 3x sine of x between x equals 0 and x equals 2 pi. So again, we'll start by graphing the function to have some idea what it is that we're looking at. Now we identify the points where x equals 0 and x equals 2 pi on the graph. So we're just wanting to find the length of the part of the curve between the two blue dots as shown on the screen. Let's zoom in so we're looking at just that part of the graph without all the extra parts there. So this is the curve that we're trying to find the length of. To find the length of the curve, we'll use the arc length formula. So for this problem, we get L, the length of the curve, is equal to the integral from 0 to 2 pi of the square root of 1 plus, now we need to take the derivative, and because y is a product, we need to use the product rule. So using the product rule for our derivative, we get 3 sine x plus 3x cosine x, and the entire derivative is squared with a dx at the end. Again, this isn't a particularly easy integral to evaluate by hand, so we will use Mathematica to evaluate it for us. On the last problem, I used the palettes to type the integral into Mathematica. This time I'm going to use the keyboard shortcuts, so you can choose which of those two ways you'd like to do when you do your assignment. But in order to do an integral using the keyboard shortcut, you type the escape key first, which makes those 3 little dots, and then you type D-I-N-T-T, which stands for definite integral. I don't know why there are 2 T's, but there are. Then you hit escape again, and that enters in the template for you. And then you just hit tab, and that takes you through all the boxes. So we start at 0, and then tab, and then we do 2 pi. Now the keyboard shortcut for pi is escape, P, escape, and then we tab. And now I need to do a square root, which again I could go to the palette, but I'm going to use the keyboard shortcut, which is to hold down Control and push 2. and then 1 plus parentheses 3. Now remember that when you're doing trig functions, you must capitalize the trig function, and then you have to use square brackets around the input. We had a lot of problems with that on the last technology assignment, so make sure that you're capitalizing your trig functions. Also make sure that you put a space between the x and the cosine in the 3x cosine x. See, look, if I don't put a space between them, it puts it all together and makes it blue. The blue word means that Mathematica doesn't know what it is, but when I put a space, then it turns the cosine into black, which it should be. So we've closed the parenthesis around our derivative, which it highlights in green for us. And then we square it, which again I'm going to use the keyboard shortcut, which you hold down Control 6, and it makes the nice power, so it looks pretty. And then you hit Tab and put in an X. I'm going to use //n in order for Mathematica to give me an exact answer. And then I hold down Shift and push Enter. Okay, so it took quite a long time for that to evaluate. I edited out the long pause while I was waiting for it to evaluate, but we get 40.8122 as our answer. So based on what we found in Mathematica, we know that the length of this curve between 0 and 2 pi is 40.8122 units. So you've now reached the end of the video, so you're ready to go and do technology assignment number 3. Keep in mind that technology assignment number 3 is also your homework from section 6.3 of the textbook. We will not be doing any of the textbook problems for section 6.3, but you will still be expected to know the arc length formula and be able to set up problems using that formula on the exam. So make sure that as you're doing the Mathematica assignment that you pay attention to the formula and how to set up problems using the formula. But you should be ready now to go and do technology assignment number 3.